Okay, so imagine a world where energy shortages are literally a thing of the past, right? No burning fossil fuels, zero harmful carbon emissions, and a limitless fuel supply pulled right from ordinary seawater. I know, it sounds like pure science fiction. But today, in this explainer, we're going to break down how humanity is actually actively trying to recreate the power of the sun right here on Earth.
To get there, we've got a pretty clear roadmap. We're going to cover powering the stars, fission versus fusion, bottling the sun, and finally, the future of fusion. Let's dive in.
Part 1. Powering the Stars, the Universe's Blueprint.
Every single second, our sun is just releasing this enormous amount of energy. It provides the light and heat that makes, well, all life on Earth possible. Scientists have been staring at this for decades, and it all leads to one massive, highly ambitious question. Can we actually recreate the power of the sun on Earth? Because if we can pull this off, we unlock massive, unprecedented power without the heavy environmental toll of fossil fuels.
And it all comes down to this one process: nuclear fusion. Deep inside the sun's core, hydrogen atoms are being absolutely crushed by just immense pressure and heat. I mean, they're squeezed together so violently that they literally fuse into helium, releasing a staggering amount of energy in the process. This exact process has reliably powered our sun, and honestly every single star you see in the night sky, for billions of years.
Which brings us to Part 2. Fission versus fusion, understanding the difference.
Now, traditional nuclear plants, the ones we have today, they rely on fission. That's splitting heavy, unstable atoms like uranium apart to generate power. Fusion, on the other hand, does the exact opposite. It forces light, small atoms like hydrogen together. So both release massive amounts of energy, sure, but fusion takes a totally different and arguably much cleaner path.
So why make the massive pivot to fusion? Well, there are three really huge reasons. First, absolutely zero carbon emissions. None. Second, there is barely any long-lived radioactive waste, which, let's be honest, completely rewrites the safety equation we're used to. And the fuel? It's literally sourced from ordinary seawater. To put that into perspective, just one bathtub of water, combined with a little bit of lithium, could theoretically power your entire life. It is the absolute holy grail of clean energy.
All right, Part 3, bottling the sun, the engineering marvel.
Now you might be wondering, if fusion is so amazing, why aren't we already using it? Well, meet the villain of our story, Earth's lack of gravity. The sun achieved fusion easily because it's so massive, it's just constantly crushing its core with gravity. We don't have that luxury down here. So to force fusion to happen on Earth, scientists have to compensate with heat, and I mean a lot of heat. They have to achieve a mind-boggling 100 million degrees Celsius. That is literally significantly hotter than the center of the sun itself. Wild, right?
At 100 million degrees, matter fundamentally changes. It turns into this superheated soup called plasma. But here is the ultimate engineering paradox. This artificial star is incredibly fragile. If this superheated plasma were to touch the cold walls of a reactor, or honestly any ordinary material at all, it would instantly cool down, and the fusion reaction would just completely die out.
So, how exactly do you hold something that is 100 million degrees without touching it? The solution is as elegant as it is complex. Powerful magnetic fields. By generating incredibly intense magnetic fields, scientists can literally suspend and control the superheated plasma in midair, keeping it perfectly trapped and away from the reactor walls.
Enter the Tokamak. This is probably the most famous fusion reactor design in the world right now. It's this massive machine that uses giant superconducting magnets to securely hold that volatile plasma inside a donut-shaped chamber. The entire goal here is just to keep that plasma stable for long enough for the fusion reactions to finally produce more energy than the machine itself is actually consuming.
Which leads us to Part 4, the future of fusion, moving past science fiction.
You know, there's this old joke among critics that commercial fusion is always 30 years away. But honestly, that's finally starting to fade. We are seeing major accelerating breakthroughs right now, fueled by billions of dollars in investments from both governments and private companies. We have highly advanced magnets today that simply didn't exist a decade ago. We're actively applying artificial intelligence to control the chaotic plasma in real time, and we have vastly improved reactor designs. The pace is moving incredibly fast.
And think about this. If commercial fusion power plants actually come online in the next few decades, the sheer impact will be staggering. Imagine clean cities and green factories operating with a near-zero environmental footprint. Picture a power grid easily handling limitless electric vehicle charging.
This kind of abundant energy could power massive desalination plants, providing fresh water for drought-stricken regions all over the world. It could even provide the incredibly dense, sustained energy required to fuel deep space missions to Mars and beyond.
However, we've got to remain grounded here. The scientific community still faces massive, very realistic hurdles before any of that actually happens. They need to drastically improve the energy efficiency of the reactors. They absolutely must figure out how to reduce the extreme costs associated with building and maintaining these complex machines. And crucially, they have to prove that these reactors can operate reliably for long, continuous periods without breaking down. So we are close, but we're definitely not quite at the finish line yet.
Zooming out for a second, human civilization has constantly leveled up by mastering denser, cleaner sources of energy. We step from wood to coal to oil to early nuclear and renewables. Looking at this historical trajectory, harnessing fusion isn't just some cool science experiment. It really appears to be our next inevitable giant leap forward as a species. For the first time ever, we are on the verge of harnessing the exact same force that powers the stars.
We've covered the universe's blueprint, the engineering marvels of magnets and plasma, and the absolutely incredible promise this holds for a cleaner future. So, knowing what you know now about how it all works and its safety profile compared to traditional fission, would you trust fusion to power your city? It's a question we might all have to answer a lot sooner than we think. Thanks so much for joining this explainer, and keep looking to the future.